Yesterday we have seen MGF, CGF of binomial distribution, and with the help of MGF we develop the answer of first raw moment which represent mean, and also we calculate second raw moment by making two time of differentiation of given MGF, and after having second raw moment and first raw moment we can get the variance by using the relation of second central moment with raw moments, and we got the answer of second central moment as NPQ, and that is nothing but your variance. So that is your yesterday's revision. Today we'll see the new topic known as additive property of binomial distribution. Firstly, see the statement and then we'll try to prove. What the statement says: if x and y are two independent binomial variates with parameters n1, p and n2, p respectively, then bracket x plus y follows binomial distribution with parameters n1 plus n2, p. Excuse me. हेलो, वालेकुम, अल्हम्दुलिल्लाह। वो अभी मेरा लेक्चर था, स्टूडेंट्स ज्वाइन नहीं हो रहे, उनको पूछा मैंने किनका लेक्चर चल रहा है। हाँ हाँ हाँ, जी 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 जी। आज नहीं, आपको चाहिए तो फिर उसके वास्ते कॉल किया था मैंने, अगर चाहिए तो आप कंटिन्यू कर सकते थे। ओ, जजाकल्ला, ओके ओके। हाँ जी हाँ जी। ओ, नो नो, नहीं नहीं, कुछ प्रॉब्लम नहीं। ओके ओके, अल्लाह हाफिज। So the statement says x plus y follows binomial distribution with parameter n1 plus n2, p. That means you have two situations. They follows binomial distribution with parameter n1, p and n2, p. That means chance of getting success is common for both situations. Number of trials, number of repetitions may be same or may be different. But for additive property, second parameter should be common, should be same. So in such situation, if you make addition of these two situations, two random variables together, then their addition also obey the law of binomial distribution, and it carries the parameters n1 plus n2, p as a probability of success. So the statement can be written by notational form: x follows binomial n1, p and y follows binomial n2, p. Then under the situation of independence, if x and y are independent, then addition of two binomial variates follows binomial with parameter n1 plus n2, p. Let us see the proof. Proof is very simple by the approach of MGF. X is a binomial with parameter n1 comma p. Then its MGF is given by mxt equal q plus p time e to the power t whole bracket raised to n1. Y is another random variable follows binomial with n2 comma p. Then its MGF is given by myt equal q plus p e to the power t whole bracket n2. So this yesterday we have seen. This is the MGF of binomial with parameter n1 comma p. This is the MGF of binomial with parameter n2 comma p. You can see only the power of bracket change. Inside bracket the quantities are same. Under independence we have from previous chapter of mathematical expectation, if random variables are independent, then MGF of sum is product of MGF. This is the property of MGF what we studied in mathematical expectations. Now replace MGF for X, MGF for Y. Now as base is same, you can add the power. So you will get MGF of X plus Y, this later should be capital, at point T equals base same, add the power n1 plus n2. Therefore, my random variable X plus Y follows binomial with parameter n1 plus n2 and second parameter coming from here, that is p. So this is nothing but additive property of binomial distribution. You have a theoretical question, state and prove additive property of binomial distribution. Now here I can put a remark. I write X plus Y. Suppose I ask all of you, can I say X minus Y follows binomial with n1 minus n2 comma p? Does it possible? Answer is not. Why? Because your binomial random variable assume values non-negative integer. That means random variable x of binomial begin from 0, 1, 2, 3, and so on. But if I take x minus y, then x minus y not necessary will be always positive. Suppose x is 0 and y is 1. So 0 minus 1 bracket will take minus 1 value, and minus 1 is not allowed for binomial random variable. So such question may ask in MCQ. X is binomial random variable, y is a binomial random variable. Does x minus y follows binomial distribution? So you have to give the answer no. X plus y will follow binomial, but x minus y will not follow binomial. Now we proceed the last theoretical topic related with binomial distribution. That is under the heading of conditional distribution of two independent binomial random variable. Statement x and y are two independent binomial variates, then the conditional distribution of x given x plus y equal to small n is hypergeometric distribution. What the statement says, you have two binomial random variables and you are trying to get conditional distribution of, you can put here x, you can put here y, doesn't matter. X given x plus y, the conditional distribution is a hypergeometric. That is nothing but a statement, you can say the result. So what we want to prove? Probability of x, the given, that means this vertical line. Probability of binomial given addition of binomial follows hypergeometric. Let us see how we get a hypergeometric, which is the last distribution of your syllabus. Now, from previous chapter, what I taught under probability, conditional probability, probability of A given B is nothing but probability A intersection B divided by probability of B. That is the conditional probability. So I use that probability x equal to small x intersection, or you can write a semicolon, doesn't matter, x plus y equal to n. Total divide probability x plus y equal to small n. Now statement says the variables are independent. So you know that if the events are independent, these are the events. If the events are independent, intersection become a product. So I write probability x equal to x multiply probability y equal n minus x. This I can do. X plus y equal to n, but what is x? X is taking a fixed value small x, so put it here. This will be transferred on the right, so y equal to n minus x. X, y are independent, so joint probability returns separate probabilities under the independence. Now, this is a binomial random variable with parameter n1 comma p, so I write a binomial formula. This is also binomial random variable with parameter n2 comma p, so by using n2 and this point, I write a binomial. How? N2 choose n minus x, that I replace y. You can say n minus x. P raised to y, that means n minus x. Q raised to n2 minus y, that means n2 minus n plus x. That we'll see in the next step. What is x plus y? Just now before we have seen additive property. X plus y is a binomial with n1 plus n2 with parameter p, so I write denominator. X plus y will be n1 plus n2, choose n, p raised to n, this is a mistake. P raised to small n, this should be small n. Q raised to n1 plus n2 minus n, not x. This is a mistake in the writing. Now let us simplify p raised to x and this p raised to y. What is y? Y is n minus x. So p raised to n minus x and this is plus x cancel. You get p raised to n and that cancel with this denominator. What about q? Q raised to n1 minus x, q raised to n2 minus small n plus x. Plus x minus x cancel. So n1 plus n2 minus n. n1 plus n2 minus n, this will be cancelled with your denominator. So what remain in the next line? Only the combinations. n1 choose x, here should be n1, n2 choose n minus x, total divide n1 plus n2 choose n. Make a correction here, it is n1. n1 choose x, multiply n2 choose n minus x, and denominator is n1 plus n2 choose small n. The rest constant cancel each other on simplification. This is my final answer, which is called as hypergeometric distribution. So what this question says, what this theory says, the conditional of binomial distribution follows hypergeometric distribution. That means x is a binomial, y is a binomial, x given x plus y is a hypergeometric. We'll see the next, the last distribution, last topic of your theory, hypergeometric distribution. What we derive from binomial, here we get similar formula. Let us see the definition of hypergeometric distribution. A discrete random variable x is said to follow hypergeometric distribution if its PMF is given by P bracket small x equal to M capital choose x, another bracket n minus m choose n minus x. This is a combinations. Total divide by n choose n. Semicolon x takes value from 0, 1, 2, continue, and where it stop? Minimum of these two values. Suppose small n is 4 and capital M is 5. So x will begin from 0 to 4 and vice versa. Suppose capital M is 3 and small n is 5. So your x will go from 0, 1, 2 up to 3. So minimum of these two values is the upper bound for variable x. Such function is to be remembered as a hypergeometric distribution. You can see if I add these numbers m plus n minus m, minus m cancel with plus m, so you get capital N. Similarly, if I add these values x and n minus x, you get small n. So the denominator is addition of corresponding values in numerator combination. That is happening in your binomial result. This is n1 and this is n2. Addition is n1 plus n2. This is x and this is n minus x. Addition is n. So that is nothing but your logical way to remember hypergeometric distribution. How to denote this? It is denoted as capital X follows hypergeometric, and this hypergeometric formula requires three constants known as parameters of hypergeometry. Number one, capital N. Number two, capital M. And third is small n. So these are called as the parameters of hypergeometry. What they stand? Number one, capital N is population size, total items under study. What is capital M? These are favorable items to the random variable, that means to your study in the respective population. And what is a small n? This is the sample size drawn from the population by without replacement. This is very important. If you draw the sample by without replacement, then it is hypergeometric. Otherwise, it will go to binomial. I told when I taught a binomial, if a sampling is done by with replacement, then you can think to apply binomial distribution. And if your sample is drawn by without replacement, then it is a hypergeometric. Where we apply hypergeometric distribution, that we'll try to study now. Real life situations, you can say practical examples of hypergeometric distribution. The hypergeometric distribution is used under following conditions. For each and every distribution, there are certain conditions. If that conditions are satisfied, then you can use corresponding distribution. Just like for binomial, every trial should result in two disjoint outcomes, labeled as success, other as a failure. Second condition for binomial is you should repeat such experiment more than once. That means minimum true trials should be there. If you make only one trial, that is a Bernoulli. For binomial, you should repeat Bernoulli trial minimum 2 times or more than 2 times. And third condition for binomial is chance of getting a success in one trial should remain constant in all the trials. Similarly, now for hypergeometry, you have to check some conditions prior to apply it. What is number one? Number one says the population under study should be divided into disjoint groups, two mutually exclusive groups. That is first condition, which is the strongest condition of hypergeometry. Second, the sample should be drawn by without replacement. This is a big mistake in the writing. Without, just now I told, sample should be drawn by without replacement. So when you will take the printout of these notes, here write without. This is wrong. It should be without replacement. Third condition is the successive outcomes are dependent. And fourth condition is probability of success changes from one trial to another trial, because under without replacement you are not replacing the selected item back, so there is a reduction in the probability. So the most important condition is number one, population should be classified in two disjoint parts and samples should be selected by without replacement. Then you can apply hypergeometric distribution. The quality control department, example of the real life, the quality control department in certain company can study number of defective items in a lot by hypergeometric distribution. How you can apply hypergeometric here? Very easily with the help of these three conditions or four conditions. Entire production in a lot will be classified in two parts. Some are defective and the rest are non-defective. So I divide lot, that is a population you can say, in two categories, defective and non-defective. Then I draw the sample from this lot by without replacement. And then I can use hypergeometry to study such type of situation. Example number two, number of fishes in a lake can be estimated with hypergeometric distribution. This is very interesting example of hypergeometry. Suppose we have a lake, and in that lake we want to estimate on an average how many fish are there by using hypergeometry. How we can proceed? We can proceed by making a experiment on a certain day. We'll go there and we catch the fish, and the fish which is caught will be marked by some color or by tying a thread. We'll do the marking on that fish. Now after marking, we'll leave that fishes maybe 1,500 or 200 in the lake. So by this experiment, what happened? By this experiment, the total fish which is in the lake divided in two parts, marked and unmarked. Then on the another day, we'll go randomly and we'll put the net in that lake and we'll catch the fish again. In this sample now, you will get some of the fishes which are marked and some of the fishes which is unmarked. So I divide my total population of fishes in a lake into disjoint part. Then I pick up my corresponding sample, and with the help of sample study, I can estimate on an average how many fishes are there in the lake. That is the way of using a hypergeometric distribution in such type of situations. We have now third example. The opinion survey can be studied with the help of hypergeometric distribution. Any type of survey where we see the opinion of the peoples, that also studied by hypergeometric distribution. Now, as per syllabus, we are not going to derive mean and variance. Just you have to remember what is the mean of hypergeometric and what is the variance of hypergeometric. Just like in previous three distributions, three, I can say four. Number one is degenerate distribution. Number two is uniform distribution. Number three is a Bernoulli distribution. And number four is a binomial distribution. In all these four distributions, we made the derivations of mean and variance. But in case of hypergeometric, we are not going to derive the mean and variance. We can do it, but as it is not a part of syllabus, we can see again syllabus. If there, we can derive, otherwise we will remember only the results. So the mean of hypergeometric distribution is small n multiply capital M divided by capital N. This much you have to remember. Variance of hypergeometric distribution is small n, capital N, same as mean. Multiply 1 minus capital M divided by small n. This multiply another bracket n minus n divided by capital N minus 1. So this is the expression of variance of hypergeometric, and this is the expression for mean of hypergeometric. This much you have to remember.